include the bending radius of the insertion tube component and the channel pressures with our modularized channel design. Furthermore, our device has the ability to be autoclaved, which improves reprocessing efficiency. This process is the gold standard of medical device reprocessing and kills virtually all bacteria or contaminants. To consider this design change, we simulated an autoclave cycle to measure any dimensional deformations with our device and assess gasket performance. The objective of the insertion tube simulation was to measure bending radius compliance with industry standards. In our case, we needed to maintain a minimum bend diameter of 120 millimeters. We performed these simulations in SOLIDWORKS with a nonlinear FEA toolbox. This workflow allowed us to simulate and perform design changes all with one software. When performing these simulations, we also set up assumptions and key requirements. Notably, our channel configuration needed to maintain a minimum wall thickness of 1 millimeter between each channel. After simulating with 30 APU, 50 APU, and 70 APU, we found only the 38 polyurethane remained below permissible internal stresses of 9.5 megapascals. This ensures the material retains its elastic properties when in use. If the material were to surpass the yield stress, it would undergo permanent deformation and transition to plastic behavior, which is undesirable. Once we reached the prototype manufacturing stage, we used these results to inform material selection. We were able to verify our simulation results by performing a bend test and observed no forms of plasticity or yielding with 120 millimeter bend diameter. So for the objective of the autoclave simulation, it was to assess the pressure and heat resistance of our endoscope design. To assess this, we need to determine if there are any major dimensional deformations that result in leaks or permanent deformation. Specifically, if the gasket percent compression decreases beyond a set threshold of 40%, a leak could occur. Again, we decided to use SOLIDWORKS, but this time with a thermal FEA toolbox for our simulations. However, when performing these simulations, we set the autoclave environment to well above the industry standards at 150 degrees Celsius and 30 psi. This allows us to test this spec with increased safety factor for our design. We also considered a 40% gasket compression threshold because it is the recommended phase seal compression amount for static seals used by multiple seal manufacturers. Our simulations revealed a decrease in percent compression of the gasket at an autoclave temperature of 135 degrees Celsius. More specifically, the gasket gap grew from a nominal 1 millimeter to a maximum gap size of 1.06 millimeters, which resulted in a decrease of 2.88% compression of the gasket. The compression percentage remains above the target threshold of 40% at standard autoclaving temperatures, thus the seal will not leak. During our prototype manufacturing, we decided to assess the performance of our gasket design. We used coupon-level testing for these experiments as the entire controller body isn't necessary to inspect sealing and gasket compression. During these tests, we assessed whether the gasket compression of our current design was feasible. Here, we can see that the gasket compression of our device is sufficient as no leaks occurred. To test for leaks, we completed an autoclave cycle with water tape indicators inside and outside of our sealed test coupon. We can verify our sealing design is successful since the indicator inside our gasket was not activated, while a control indicator outside the gasket was activated. The final simulation performed was a fluid first principle analysis on our channel system. Each channel component, namely auxiliary water, air water, and suction, has set industry specifications. We used Excel and the computational solver add-on to solve for each channel pressure. To measure these pressures, we formulated the channel and fitting relations with Bernoulli's equation. As part of our assumptions, we considered minor losses from our fittings and major losses due to the friction of our channel walls. Modeling fluid flow through channels demonstrated that our design is viable and allows for the normal function of flow through the channels based on current industry standards. Our model validates that even with our changed channel design, we did not impose issues regarding channel functionality. Again, we were able to validate our model during the prototype assembly phase. We tested channel pressures with pressure gauges and recorded precise and accurate specifications, indicating the validity of our model. Our air channel model achieved an average absolute error of 3.93 psi. This plot shows the simulated and measured pressures for our air channels. Our x-axis indicates the pressure coming from the pump, and the y-axis is the final output pressure after passing through our endoscope channels and fittings. Results from the water channel indicated even better results, with an average absolute error of 0.239 psi. After performing these simulations, we were able to leverage these results for several key design choices. First, our channel layout and insertion tube can withstand worst-case bending. Our heat and pressure simulation demonstrated that our gasket design is robust and can withstand an autoclave environment. And our fluid model showed our channel integration allows for suitable pressure outputs for all functional channels. As a whole, these simulations provided us with useful insights for our design iterations. Results from the simulations indicated if any design changes were required. It also allowed us to prototype in a cost-effective manner, which was required in our budget-constrained setting. We are Pedalos, and we are redesigning the endoscope for better clinical outcomes. Thank you.
Alrighty, thanks guys. Any questions from the judges?
Can you go back to the slide where you were showing the fluid? This one, yep, here. So you have a sleeve over it though as well. Did you model the fluid flow past here, past where your arrows are?
Yes. So the sleeve is actually 1.25 meters long, and we take that into account in our first principles math. We just didn't show it here.
Okay.
The way we do that is like it's essentially Teflon tubes that are overmolded with PU on top. So we're disregarding the effects of the PU because they don't really come in contact with the fluid, and we're taking all the material properties of like standard Teflon tubing that you can buy from multiple vendors, and the lengths as well as all the fittings and their impact on the entire system.
Okay. And so these output boundary conditions are at where you're indicating here, the arrow markers, or at the end of that long tube?
At the end of the long tube.
Okay.
Quick question for you guys. I'm not super familiar with endoscopes in general. Can you just quickly sort of summarize, like, what are the main differences that distinguish the approach that you folks have taken with this compared to commercially available ones? I'm just trying to get a sense for the scope of the sort of redesign that you've done.
Mm-hmm. Sure. Isha, do you want to go back to one of the problem slides? I think at the last one. So during our analysis, we found that essentially, even one more back, Ethan, a couple more. There. So when we were looking at the reprocessing steps of endoscopes, essentially what they had to do was clean the entire device. And the way their channels are designed is that all their channels are reusable, and they use these long brushes to essentially try and clean out any debris inside of it. And from that, we found that there's a lot of contamination from patient to patient, and that was the key issue with patient infection. And then looking at the FDA review, what they said was to try to move towards disposable devices or just try and redesign the endoscope completely. So from that, we understood that the channels were most risk of contamination. So we tried to redesign it for a disposable component instead of a reusable one.
Another big thing is that all the channels on a traditional endoscope, they're buried inside of the device. So there's actually no way to get to the channels. So like if you were trying to inspect a 1 meter long tube that is 2 millimeters in diameter, it's basically impossible.
So I guess if you go to the next slide where you've got the drawing of it, so the big difference then, your tubes are moved to the outside and are removable and disposable. And then the actual sort of like remaining wand part is the setup that you're putting in the autoclave. Is that true? Okay.
Yep.
So I guess with kind of current solutions, like what fails? Why aren't they able to go into an autoclave?
One of the big reasons they aren't able to go into the autoclave is actually the adhesives that they use to hold together the device. And these adhesives are used to hold down those tiny little channels like internally of the device. So they can't actually overmold it like what we're doing because there's complex like mechanisms inside of that device, so it would be impossible to mold. And the other reason is Actually, that's basically it. Yeah.
No, that makes sense. Thanks.
I have a quick question. I like your PTFE bend radius experiment that you did there. That kind of proves that you can match what the existing technology uses. One thing, and at the risk of sounding somewhat explicit, the feel of this device inside, um, I'm assuming there's some force from the spring back effect of actually bending the tube. Have you kind of characterized that versus what the kind of gold standard is right now in these types of devices?
Sure. So getting those actual numbers for, like, let's say how much force it takes to make this radius is pretty difficult, given that we don't have like a $35,000 endoscope to play with. But that is actually a feature on traditional endoscopes that they can control. So they can control how stiff this meter-long tube is with a dial, and there's a steel cable that basically like tensions the entire line as it goes through the body. And
Are
all
you
we can
doing
really
that
say
with internal
anecdotally
pressure?
here.
Are you doing that with
Uh,
internal pressure?
No, we don't have that implemented in our device, just for complexity sake, and it doesn't really impact like what we're trying to demonstrate, which is it's easier to clean. Um, but yeah.
All right, thank you.
I have a quick question if I can. I'm Steve Lambert. Sorry I was late. I was waiting for Chris to let me in, but apparently I had to actually let him know I was there first. I didn't realize that at first. You said in your impacts that gasket can withstand the autoclave environment. Was that based on simulation?
Yep.
And what did you simulate to verify that it would withstand the environment?
So all of the materials that we buy are from vendors that rate like the temperature setting. So we know all if we just threw a pile of these materials into the autoclave, they would all survive. The thing that we care about is how much the gasket groove expands due to thermal stresses inside of the autoclave. And we want to make sure that the amount of compression that we're putting on this EPDM rubber is enough to maintain the full seal in all the temperature ranges. So we were looking for the growth in that gasket groove over a sweep of temperatures, which is the data on the previous slide.
Okay.
Yeah, so you can see like we start out with 44%-ish compression at 0 degrees, and then we did a sweep of simulations over different temperatures to see how much does that gasket decompress. And if we maintained a compression rate of greater than 40%, which is a standard spec that most gasket manufacturers recommend, then we assumed that we would be safe. And then to verify that, we printed out some test coupons. And then if you go to the next slide, Ethan, you can see that our gasket like compression ratio and expansion that we see is enough to keep the indicator sealed throughout the entire autoclave cycle.
Does it actually have to be sealed during autoclave or once it cools down is it being used?
So it needs to be sealed because we have electronics and a bunch of other goodies inside of the actual device, and that would be a pretty big corrosion risk if we were to just like, let's say, take out the sealing system.
Okay, thank you.
Yep.
Any other questions for them? We still got a minute or two left. Anything else that you guys want to tell us that we haven't asked about? Alrighty.
That was a very well presented presentation, I thought. But you did go through a lot of information very quickly. So
Cool. Well, thank you so much. And best of luck with the rest of the capstone cycle and your 4B term.
Thank you
Thank
for
you.
having us. Good night.
I'm glad we did that one after lunch.
That's a tricky one.
I'm glad we did that one after lunch.
Yeah. Let's see.
I'm glad I missed the first couple slides.
Hey guys. How are you
Hi there.
doing?
Well, thanks. How are you?
Doing pretty well. Anyone else expected from your group, or just the pair of you?
It's just the two of us today.
Perfect. I guess we'll kind of kick things off with a quick round of introductions from the judges, and then hand things over to you guys for the presentation. Steve, do you want to start us off again?
Hi guys, Steve Lambert. I'm their instructor for ME482.
I'm Jeff Abshoff. I work at ANSYS in development.
I'm Andrew Rooch in Mechanical and Mechatronics Department.
And I'm Chris Rennick from the Ideas Clinic. So with that, if you guys have a presentation, feel free to share your screen. We are right on 2:50, so I guess in about 9 minutes, we'll give you a 1-minute warning, but otherwise, it's all yours to present.
Fantastic. Thank you.
Thanks.
Minimize this here. Are you guys able to see the presentation?
Yep.
Excellent. Okay. Well, thank you very much for joining us today. I am happy to have the pleasure with James to discuss with you some of the analysis work that we've done on our final capstone design project. To, I guess, jump right into what our project is. James and I and the rest of our group set out back in September to tackle the challenge of ventilation inside apartment buildings and houses, specifically in urban settings. And one issue that we found from personal experience that has been particularly relevant is that we love having our windows open in the summertime, allowing a fresh breeze to come in, giving us a bit of a connection to the outside as well. And one challenge that is always coming with this ventilation is urban noise. And so we really wanted with this project to target a product that was able to provide this same experience of having the windows open in the summertime. This is especially effective in buildings that don't have air conditioning, or for those who do just prefer having windows open versus AC. I think you can relate to that when you're in your car. Sometimes it's just nice to put the windows down and feel the breeze. And so that's what we really wanted to do with this project. And so we're looking to create a device that damps the incoming noise that's particularly loud from urban areas, and still give that fresh air feeling, the ventilation, and the smell, the sounds, or sorry, not the sounds, but we wanted to exclude the sounds. And so really just to give you a feel, this is jumping a little bit farther ahead into what we've come up with. We've down selected to a window insert that works particularly with a sliding window, and it's a box that fits in like a window mounted air conditioner, but it is not an air conditioner in the sense that it doesn't use electricity to cool the air. It's just drawing in the air from the outside, and has a lot of passive sound damping technology inside it, and that's what we've been working on. So for this application particularly, we wanted to target traffic, conversation, and construction noise. We thought those were the most relevant in urban centers, and so that overall gave us a frequency range target that we wanted to reduce the sound intensity of about 150 hertz all the way up to 5,000 was our goal here. And so we also, just through our research, found that typically our busy street noise was anywhere from 60 up to 80 decibels, and so we performed all of our sound analysis within that range. I'll let James take over here.
All right, yeah, jumping into the approach here. So initially, our objective, we started with some concepts for this magic device, as seen on the left here. And then, so these use different sort of technologies that we found through different research, looking at things like mufflers for cars and things of that nature, and then putting it all into this box that'll fit into a window. So then starting there, we did some simulation work for both flow and acoustics. And then just doing some foreshadowing here, we ended up picking the long tube perforated venturi concept. And then starting with that, we did some more detailed refinements to make sure we had the best trade-off between both flow and acoustics. So then here's the setup for the acoustic simulations that we use. So the software we used for this was ANSYS Harmonic Acoustics. And the equation that it uses is seen in the bottom left there, the harmonic acoustics fluid structure interaction equation, which really allows us to do exactly what we want, see the interaction between the air and the box that we're using, and then to get a full sound reduction from the inlet to the outlet ports of the device. So this device that you're seeing here was a validation build that we did, just something simple to make sure our simulations were valid so that we could use them to do our iterations on. Sorry, could you just jump back there, Corson, for a sec?
Oh, sorry about that.
No problem.
Sure, how to jump backwards. Yep.
Yeah, just to explain the setup a bit more, the left side was the inlet port, so that air face was defined as the inlet port, and then there was a sound source applied to it. And then both the inlet and outlet ports had radiation boundaries so that the air traveling to that face was just allowed to escape the model. And then the Q equals 8.24 times 10 to the negative 4 there. That's the mass source that is actually the sound source. The way ANSYS works is that you have to apply a mass source there to act as the sound source, and this value equals about 80 decibels. Now, good to go on to the next one.
Awesome.
So yeah, like I was saying, we did a validation here to make sure our simulation was valid in the real world. So you can see in the top left, we did sound reduction for both the physical test and simulation. And you can see it follows a similar trend to physical test. We just missed a few peaks and valleys there, and this is further shown in the right graph. You fit a cubic trend line to both the physical test and simulation, and they follow the same path, starting a bit lower at the lower frequencies and then getting higher as we increase the frequency. And then in the bottom there, you can see the average sound reduction is quite close. So we deemed these simulations as valid, especially because our simulations are slightly under predicting the sound reduction.
Awesome, thanks, James. And then on my side, I was using SolidWorks flow simulation for the all the flow dynamics that were involved with this project. And so really the way that SolidWorks flow simulation is working is it's solving the Navier-Stokes equations, and it's evaluating them based on the fluid state equations that are put in, and I set boundary conditions within the software to be able to properly predict the scenario that we're going for. And so what you're actually looking at here on the right is it's a hemispherical environment that we were modeling, and so the entire environment was meshed. It had a radius of 1.5 meters, and that entire hemispherical surface was deemed to be environmental pressure, and so we thought that 1.5 meters was enough to say that we're unaffected by the flow is unaffected at that point, and should be more or less mixed with the room flow. And then we set a fixed flow rate into the box, and that was based off of fan capability, and that we had that manufacturer data in order to run that properly. And so yeah, really, actually, I'm just going to jump ahead into how we actually used some of these like a little more practically in the details of it. So as James mentioned, we had 3 different concepts. We did some physical testing, and we supplemented that with flow simulation and acoustic simulation. And yeah, what happened here, so you can see that we performed that for each of these different concepts. And what we really found in terms of the results of this was that the 3 concepts had huge differences in terms of their sound performance, and that the flow performance was not really as much a limiting factor for a lot of them. And so we saw here that really the long tube perforated venturi tube, based on the ANSYS simulation results, had a lot better performance in the low end of our targeted frequency, which is the entire frequency shown here, and that the other two concepts showed pretty low performance. And then this was also supplemented with some experimental tests that showed the same results. So James, do you actually want to jump in here and
Yeah, sure. I can just quickly fly through these. So yeah, now that we chose our design, we made some changes throughout to improve both flow and acoustics. Go to the next slide. Maybe I see we're at 3 o'clock now. Just quickly run through. So yeah, this was the initial one. We made some flow improvements by adding some radii and fins at the outlet there. And then maybe on to the next one.
Yeah, the only thing I want to say here, actually, and perhaps we can skip the next one, is that this iteration, we were really going for a more smooth velocity plot, as well as the pressure plot. And we still saw a lot of vacuum in certain spots. We didn't like the flow around this canvas sheet, which was supposed to be an acoustic device. And we also saw a little bit of chattering in terms of the pressure plot around here. And so when we then let's see, and then we jumped to the next iteration, we smoothed some things out, changed some values based on these results, and we found we got a much better distribution of pressure and flow, and it also helped us to actually end up removing this feature. We determined that it was something that wasn't going to be worth the acoustic benefits, given its hampering on our flow predictions. And those are iterations there, and I know we're at time now, so I won't go into the detail of how they changed, but we were satisfied with the acoustic results afterwards. Once we then simulated each of these iterations that were mostly had changes based on the flow simulation that I performed, and then James came and validated the final acoustics of it. So both these tools were extremely useful for us and saved us a lot of time in not having to build physical tests. And it was also very repeatable.
Cool. Yeah, thanks, guys. Any questions from the judges?
So one of your slides, you showed the mesh for, I think, the acoustic, one of your acoustic runs. And I didn't see a mesh for the fluids, but what did you learn about with your meshing and the impact that has on solutions?
James, do you want to answer that one?
Yeah, sure. So I noticed with the acoustic simulations, the meshing was quite difficult. We did add foam on the interior faces of these parts to try to damp as much sound as possible. And with that, we had some very thin features. And the meshing was really difficult to do those thin features. So sometimes to accommodate the meshes, they had to be thickened slightly, or we had to cut away some different areas to basically accommodate those small features. But yeah, I noticed with the simulations, I had to do that on the validation sim as well. So that seemed to be okay.
And one last thing I'd like to add to that too is I'd like to actually point out an error that was caught in the flow simulation in this plot actually on the bottom right with velocity. You'll notice that through the inlet of our Venturi tube, which is just a tube with two conical tubes that are perforated, as you can see up in the top here, there's a cross section of it. As part of the meshing for the or to, I guess, improve the calculation speed and simplify the meshing on the flow sim, we decided to, in our first simulation, opt out of the perforations and thought that we made an assumption, a preliminary assumption, that the small perforations would have less effect on flow and more effect on acoustic performance. And so it was something that we made sure to have perforations included in full detail here, but we didn't do that here. And what you'll notice is that we reach some ridiculous air speeds. I mean, this is about a half-size PC fan, and we're reaching, suggesting that we would reach 50 meters per second, which is ludicrous, and we recognized that right away. And then as soon as we went to, so that was the same one, and then I'd say it significantly improved as we got to this point. So that was just one thing I wanted to point out, was that that it was important to include that detail.
I have a quick question. If you can go to the slide where you had the frequency spectrum for all three designs.
There were these three iterations, or would you like the previous
the three different designs? Yeah, so it seems like your first sound maze kind of just truncates the low frequency sound, which is kind of what you expect, because there's a characteristic length from those vertical baffles that you're getting in the flow pattern. The triple perforated venturi kind of is a mix of the two, but I want maybe the multimodal approach and all of the different elements you've incorporated into the design for the long tube perforated venturi. Explain why it's such a flat sound response curve there.
Such a flat response for the...
Yeah, was that kind of just by accident, or was that intentionally tailoring each of those different devices inside the larger component?
Yeah, this one, or yeah, of course, and you go ahead, I think.
If you don't mind, I can even talk a little about the long-term tube perforated venturi, the concept we ended up going with here that had the best performance, which is in the dark blue here. This was actually something that was born out of these two. And we also saw this in some of our experimental testing, which included testing different kinds of automotive mufflers. We tested a few other plywood concepts that we had built in our shed. And we really liked the excellent performance of the sound maze up here. And we wanted to, I think what happened here, the reason we had such a flat response on the triple perforated venturi was it had to do with the diameter and overall the amount of airflow that was capable of passing through this one. Really, the venturi tubes do have play an important role within the device, and we validated this later on and through physical testing, and we were removing components and testing out our acoustic performance, and it showed that this was a vital contributor to sound reduction. But I think what happened here with this one, and the reason it was so flat, was that we don't have consistent cross-sectional area. What we did was we made a consistent volume of design space, and what that ended up doing was because the venturi tube was then you could line three of them up, you effectively just cut three holes in a big box, and it was much more similar to the window being wide open. And so I think, given the geometry and the proportions and just the fact that the venturi tubes were on their own, is the reason that we got such a poor sound reduction performance out of this.
All right, that makes a lot more sense. Sorry, I think I confused them because the colors weren't coming through on the presentation, but that explanation helped. Thanks.
Okay, awesome.
So for the long tube perforated venturi, that one is powered, like that one's got a fan in it, but the other two are passive. Is that true?
Yeah, I'm glad you brought that up. Actually, as we had developed the sound maze and the triple venturi, we were still toggling with the idea of, do we want this powered or do we want this not? And of course, there's a lot of simplicity that comes in not powering the device. But what we just learned, and actually the triple venturi and this simulation really helped us make the decision that powered was necessary, because we were going to have a device that was so open, such as the triple venturi, in order to achieve the flow rate from just the natural pressure differential from outside environment to the inside of the room. And so once we saw that this concept couldn't hold up, and that even here that this sound maze was likely too restrictive to have natural flow come in, unless it was powered somewhere else in the house or driven somewhere else in the house. We realized that in order to achieve our target, which was an overall average sound reduction of at least 10 decibels on average, we were going to have to go with a powered option. And so this actually really helped us make that decision. And so as these concepts were created, we knew that, okay, if this is going to be the viable one and this one performs well, then we're going to have to power it.
I guess two things come to mind, and they're sort of outside of the scope of this in some sense. But one of them is I'm curious what the impact of larger and smaller fan diameters and then larger and shorter boxes would have. You're going to see, like, the larger the fan, it'll get a little quieter itself, but the pressure isn't going to be the same. There's going to be some sort of differences that drives. Who knows what effect that has. And the other one, I think there's an opportunity there to, I think, add a filter. A lot of this urban environments, it's a lot of exhaust fumes and things that are coming off of cars on the street below. And again, I'm kind of curious what impact that would have on things. And I think it's maybe an opportunity to kind of add a feature almost, but again, we're kind of so near the end of your capstone. I think it's probably outside the scope of this, but yeah, curious what your thoughts are.
Yeah, absolutely. Yeah. James, if you don't mind, I know I've been answering these a lot. Do you want to jump on this one?
Yeah, sure. We actually did end up doing a bit of a filter, at least. This design we have right here was our first prototype that we built. And we started with a 60 millimeter fan, and it was quite noisy to get the amount of airflow that we wanted. So then we ended up switching to an 80 millimeter fan. And with that, yeah, we could really reduce the sound that the fan was producing because in ambient conditions, you could really hear that fan. But then now that we've transitioned to the 80 millimeter in ambient, you like barely even hear this thing. And then we've also included on the inlet at the top left of the screen there. I don't know, maybe you could hover your mouse over that.
Yeah, this inlet here.
We've actually added a shroud that the fan's going to basically sit in front of. And then with that shroud, we included a filter and a protective screen in front of the fan so that no one can like stick their fingers in there and stuff to try to keep bugs out and everything. And I don't know for sure if I don't think this filter would filter out like exhaust fumes and things like that. But yeah, that could definitely be a next step to improve the device for sure.
Absolutely.
Yeah, I think with that we've run a little long, but yeah, thanks so much, guys. Great presentation and good luck with the rest of your capstone.
Thank you.
Thank you very much. It's been a pleasure.
Thanks. All right. Afternoon, everybody.
Hello.
Hello. How are you all doing?
Pretty good.
Pretty good. I think we'll start things off with just a quick round of introductions of the judges, and then we'll turn things over to you folks for a 10-minute presentation, and then we'll follow up with some Q&A. So Steve, I guess if you want to kick off the intros.
Hi, I'm Steve Lambert in Mechanical and Mechatronics Engineering.
I'm Jeff Abshoff from ANSYS in development there.
I'm Andrew Gergruch from the Mechanical and Mechatronics Department.
And I'm Chris Reinick from the Ideas Clinic. So with that, we are at 3:13. So I'll give you folks a 1-minute warning in about 9 minutes from now. But if you want to share your screen and get started, go right ahead.
Sure, I'll share my screen right now. Are you guys able to see? Yeah, okay, good. Awesome. Yep. I'll just start off. Okay, cool. Hi. We're oops. Ah. Oh. Hi. Sorry. We're Group Smart Switch. We're in EC. We're all in electrical and computer engineering, and we're Group 62. And my name is Bryant, and the members with me are Zach, Martin, Eric, Victor, and Hannah. So let's get started.
Yeah, so the problem that we're looking to solve is currently a lot of people are starting to adopt electric vehicles, but the charging infrastructure behind it is not ready. Typically, most households have a service current maximum of a roughly 100 amps, and this limits people to the number of cars they can charge at one time. So for example, if you have 100 amps available and a 20 to 52 amp external load, which obviously varies with how much your house is currently drawing, you have an option of either using one large EVSE and only charging one vehicle at a time, or you can have multiple smaller EVSEs that each are rated to a lower current rating. This is problematic because either you charge one at a time, which requires you to get up in the middle of the night and swap them around, or charge two vehicles slowly. This is obviously not optimal. So what we're looking to do is create a smart load balancing electric vehicle charger that allows us to use the maximum remaining current that your house is not using and dynamically allocate it to any EVSE nodes that you have at your network at the moment.
So our product Smart Switch intelligently distributes battery charging between multiple vehicles. This will make optimal use of the power that's available at the time, and it guarantees users with multiple EVs that their vehicles will be sufficiently charged in a timely manner.
So the charging algorithm that we've developed is written in Python, and it's a continuous loop that evaluates all the cars and creates a priority queue in terms of which cars get to charge first. So a statistical approach using z-scores of various factors into vehicle travel patterns will be used. So the z-scores will be computed for the distance traveled, the available time left to charge to each car, the real-time state of charge value for each car, and the user preferences, and what we call that importance in terms of where the vehicle ranks amongst a group of cars. So all of these values will be calculated with z-scores, which we normalize through the z-score approach, and then recalculated and then re-added to get the final priority queue number for each vehicle. And then we'll use that to prioritize which cars will be charged first. And yeah.
So for the current sensor module, the purpose for this module is monitoring the total current drawn from the house. And the module contains a microcontroller. We use Arduino, and also contains a current transformer. This is a built-in resistor transformer, a LoRa module, and an analog to digital converter. So for this program, we choose the correct scaling factors to measure the current. The maximum current from house is usually around 100 amps. So we set the scaling factors to measure the maximum is around 110. That should be big enough for our project.
But within the EVSE itself, there's two main subsystems, the front panel and the pilot signal. So for the front panel, we desired to have a LCD display, a rotary encoder, several buttons, and indicator LEDs. This is a little bit problematic because the Raspberry Pi only has a certain number of I/O pins available. And because of that, we had to go ahead and design our own I2C LED driver and display driver. And to do this, we used initially hand calculations with KCL and KVL to determine the appropriate op-amp gain for the LEDs, as well as to current limit, because the I/O expander that we're planning to use has a maximum current sinking ability of 10 milliamps, and we used the voltage buffers and op-amps to get around that. We used LT Spice to confirm the functionality before PCB fabrication, just to make sure that everything was working as expected.
With respect to the pilot signaling, the protocol we're using, J1772, requires the use of a pilot signal to indicate the available charging current and to indicate the status of the vehicle. The generator circuit was simulated using LT-Spice to confirm functionality, and the circuit is based on a comparator integrated circuit. After we assembled the circuit, we used tools like multimeters and oscilloscopes to validate that the circuit was working. And we also used those tools to validate the front panel subsystem as well. In this screen, you can see this is the prototype that we built, and it has all of the front panel and the pilot generator circuits inside it. So for the pilot signal generator, it uses a LT1716 comparator integrated circuit. And on the left is a schematic we drew up in LT-Spice to simulate the operation of that pilot signal generator. And on the right, you have a transient analysis screenshot, which shows the 1 kilohertz square wave with 12 volts amplitude, and the resulting voltage time graph is plotted on the right.
On the software side, we have React app hosted on Google Cloud Platform with Node.js as backend with MySQL databases. And the reason why we use GCP is because we want our app remotely available at all times. And we use React to develop our web app because it is a very fast and simple framework. And we also use React and Node.js together as front-end and back-end, respectively, because they use the same programming language, which is JavaScript, and it's easier for the developers to develop and maintain. And we have MySQL as our database because it is widely development supports and it is very easy to use and it's compatible with Node.js. And we also use Table Plus, a database management software, and Postman is an API platform, and we use them to implement and test our backend to make sure our API works correctly. And on the EVSE side, we use React to develop our web display for the same reason. And we use Python script for GPIO of the buttons and WebSocket because they have better supported libraries. And the communication between web app and Python scripts are handled by WebSocket, so we can have real-time interactions between the buttons and the web app. And we also heavily rely on print statements and browser development tools for development and debugging.
So the final simulations are conducted for multiple vehicles to indicate whether the cars were charging, with the terminal displaying at least as you can see right here, displaying at least one of the cars connected to the charger, I guess. And then due to the lack of available EVs, since we aren't actually charging any actual cars, we've used the lamp here on the right side to simulate a car being charged. So if we are sending current through the electric vehicle charger, the lamp will turn on. And then we use an accelerated charging model in Python to simulate the other electric vehicles and so forth.
So our product Smart Switch overall makes charging multiple EVs more efficient. And with the rising sale of EVs, we believe there are many opportunities for this product to expand in the market.
And that concludes our presentation. Thank you.
Alrighty. Thanks, everybody. Quick clarifying question for you. Does your device, is it the charger itself? Like, is it the thing that's mounted to the wall of my garage, or is it mounted at the panel? I kind of didn't quite understand that part.
So it's actually both. There are a few different aspects to the Smart Switch system. The photo on the left of this slide is the EVSE. That's the charging station, which is mounted in your garage. And the current sensor module is mounted in your breaker panel, and that monitors the current consumed at a given time in the entire building.
So in the case then where I had, I don't know, say 2 EVs that I was charging at the same time, I would have 2 of these devices in the garage, or does one of them then have 2 cables?
You would use one EVSE per each vehicle that's in the garage.
Okay. So how are you, and I guess that's the sort of cloud services you're using are to help sync all that data together into one place?
Yes, so we host our web app on GCP, and we also have our database set up in the GCP as well. So when user inputs their vehicle data, it will store in the database in the cloud server, And for our devices, we just retrieve the information from that cloud server.
So the other thing I wanted to ask about, the calculation you were doing to figure out which car was going to get charged at any one time, you said it was looking at four things: distance traveled, available time to charge, state of charge, and user preferences. I understand how you could collect user preferences. You've built this web portal fairly easy to do. How are you pulling in those other three pieces of information?
Okay, also I'll answer this question. So for distance travel, it's actually an estimate by the user how far they're willing to travel and on an everyday basis. So obviously, as this is a prototype, we just enter whichever values the user would like. But obviously, in the future, like if you are going to work to a certain location every single day, that distance would not change, right? I guess in a day-to-day basis, or at least from Monday to Friday. As for the available time to charge, we actually pull the time that the user wants to leave the house. So say you're bringing you're bringing the car at say 6 p.m. on the evening, and then you said in the web app, okay, I want to leave at 6 a.m. the next day. So we're actually polling the time continuously to measure how much time's left for each vehicle left to charge. So for each car, there'll be different amount of time. Right? So say one car wants to leave at 6, one car wants to leave at 8 a.m. So there'll be that difference of that 2 hours essentially. And then as for that real-time state of charge value, we actually used so we actually simulated how long it takes to charge each vehicle. So say you want to charge to a certain percentage. We actually use something called we actually simulated how much state of charge, or how much battery we have to charge the vehicle to get to this distance. And then based on that, we'll update that state of charge value as time goes by. So after say 1 hour, it'll update maybe like 5%, for example. So there's some sort of scaling factors that we've done to simplify this a bit.
So do you need information then about the car itself?
Yes. So each car so our product is actually like our product would have like a database containing some of the more popular electric vehicles. So each vehicle will have some sort of data sheet assigned to it, like how fast they consume energy for a certain distance, for example, right? So for example, like a Tesla would say, I'm not very sure, but like on the top of my head, I can't read off any values. But for example, they say, yeah, we'll take in like a few megawatts for like every 10 kilometers, for example. Okay. And then we estimated that. So say we have like a 50 megawatt hour capacity, that would be the 100% charge. And then we calculate based on how far you would travel and whether you're traveling in like an urban environment, whether it's on a highway, so things like that. A lot of that information is provided by the vehicle manufacturers.
Yeah. Any questions from the other judges?
Sure.
Yeah.
Go ahead.
Go ahead,
Steve.
Go ahead, Andrew.
All right. If you have multiple vehicles connected, so do you cycle between the EVSE nodes to kind of balance battery health or the cell temperatures? Like, can you add more priority queue attributes to charge in a smarter way instead of just switching between things based on user preferences? Can you take more attributes to kind of distribute the thermal load or distribute some of the usage on the system better?
I can take this one. So for the purpose of our prototype, our model was relatively simplistic because we don't have a EV to work with. But in the case that we do, for example, with the Tesla or a Nissan Leaf, all those offer APIs that show battery health as well as charging the temperature of the battery and other metrics that we can use to further expand our charging algorithm.
Okay, and as part of that charging, my understanding is that batteries will take bulk charge or top-up charge, trickle charge, and I presume the EVSE will take that into account. But does your system account for things like that as well, different levels of charging depending on the state of charge of the battery?
Yeah, I'll take that question. So actually, yeah. So there are actually things called charge curves, like I think you mentioned the trickle current, what was it? Yeah, some of the other different currents for the cars. But I think a lot of those information wasn't very readily available to us. I think they're more proprietary to vehicle manufacturers. So we've kind of just mocked up different current levels. Say after a certain percentage, we'll reach the trickle charge current, or after say at a certain SOC, it'll require this amount of current. So we kind of just simulated a lot of these processes, because at least just to show some sort of realistic, like make it as realistic as possible. But obviously, without that information from vehicle manufacturers, it's a bit hard to get that going.
Okay. And in terms of your algorithm, do you switch, first of all, how fast do you switch back and forth between two different cars? And how do you switch? Is it a control signal, I presume, to the EVSE? And it seems as though you're either charging one or the other. Can you
So, okay, yeah, I
charge them
can
both
further
at the same
elaborate
time?
on that. Yeah. So it actually depends on how much available current is available for the cars. So say, for example, in your house, so you turn on your stove, your heater, your washer, like things that are high demand and load, there actually won't be enough current to sufficiently charge all these cars. So maybe the cars won't turn on at all, won't be charging at all because they don't have the required current. So, but like say if you're sleeping and none of the appliances are being used, then there'll be a more available amount of current left to charge those vehicles, right? So, and at that point, then we will calculate how much current each car needs at one point, and then see if there's the available current to charge it at that point.
So you can charge both simultaneously?
Yes, we can. If there's enough current, yes, we can.
How do you control how much current? Can you dial down one and preference another, or is it on off?
It's more just it's based on what the vehicle wants. So we actually the vehicle itself.
Can your system do it?
Yeah, I think.
So I think there's a misunderstanding of how it works. So the EVSE indicates to the vehicle how much current is available at that station, and the vehicle detects that and has the liberty to consume however much current it wants within that constraint. So suppose that for a given EVSE, 20 amps were available at one time. The EVSE would indicate that 20 amps were available, and the vehicle could consume any current that it needs within 20 amps. So it could have the choice of taking between 0 and 20.
Okay, and your system accounts for that and allocates more current to the other EV if the first EV doesn't need 20 amps?
Yeah, it does.
And how does it actually control the amperage or the constraint essentially that the EVSE sends to the vehicle?
It doesn't. So the protocol requires that the vehicle does not consume more current than what is available. And the current that is available at a given EVSE depends on the priority queue that we described earlier.
Okay, but you control that amount that's available.
Yeah, the EVSE dictates to the vehicle how much current is available.
Right, and you dictate to the EVSE how much they can use.
That's right. The charging algorithm will determine that amount.
But if what electric vehicle one chooses to only use half of their allotment, would your system then bump up the other one?
It would, yeah.
Okay. Thanks.
Jeff, any questions from you? I think we maybe got a minute left.
Yeah, one thing that came to mind is, so people who use this right away might program it in such a way that there's always competition. My wife and I want to leave at the exact same time. We have the exact same vehicle. We are competing. We drive the same distance because we drive to the same location, but we don't carpool for some reason. Like, how are you going to stop it from being like in this switching back and forth continuously to make sure that both vehicles are not swapping that way, so that they're regularly drawing power properly?
That's a pretty good question, but I think overall the how do I say this? Well, if you guys are both going to the same, the z-scores calculator will be the same for both vehicles. They will be both 0, I think. So at that point, it will just take into account the importance where you want to rank the vehicles.
They're equally important, right? Because I didn't program it at all. I just bought
So
your thing,
you can't.
and I.
So our algorithm right now says you can't duplicate some of the factors such as importance, the ranking. So if you set one as 0 and you set the other as 0, the first one would be like a null value. It'll be and you have to reset on the app itself. So we're trying to make it as how do I say this? As like charge as smartly as possible, but obviously there will be some discrepancies among users, I guess. But I think yeah.
That's probably a good thing, having that importance value available, because then it allows more customizability. So then you can talk to your wife and say, okay, I'll take importance one day, and then you take importance 1 the next day. That's also one of the key reasons why we had it.
Yeah, and then the follow-up question, I guess, is if vehicle A is importance 1 and it has a lot of charge left, it might get more of the allocation, but vehicle B might be like really dead, and it's on fumes, so to speak, if it was a gas vehicle. Does that factor into your?
Yes, actually, sorry, actually, so actually, what all these factors, they actually all have a weighting of 0.25.
Okay.
So when we add the z-scores of all of them, so yeah, they'll be all equal weight currently as how we've designed it. So obviously, if one has a lot of real-time state of charge, then that value of that z-score will be extremely high compared to one that's low in state of charge. So that will factor into the priority queue. So say, for example, like your preference, this is not the be all, like that's not the only factor that will affect the priority queue, but it'll be all these 4 factors. So yeah, it'll try to balance it as much as possible, essentially, like which cars should charge first.
Thanks.
Alrighty. I think we're out of time, but thank you so much, everybody, and good luck with the rest of your capstone project.
Thank you.
Thank you.
Yeah.
Thank you.
All right, next group. Good afternoon, everybody. Welcome. Sorry we're running a little late. I think we'll do a quick round of introductions of the judges, just so you know who all of us are, and then turn things over to you guys for the presentation. So Steve, if you want to kick things off.
Steve Lambert, Mechanical and Mechatronics Engineering.
Sorry, my camera's off. Jeff Abshoff. I'm from ANSYS, work in development there.
Andrew Griguch, Mechanical and Mechatronics Engineering.
And I'm Chris Rennick from the Ideas Clinic. So with that, we are at 3:37. You folks have 10 minutes for a presentation, and I'll send you kind of a 1-minute warning in the chat. But feel free to share your screen and kind of take over from here.
I'm sorry, we are group 2, and I think there's another group that's missing out with us.
I think we were scheduled to present at 3:30.
Oh, I may have let too many people in. Is that what you mean? I think we should be on the P6PY group at 3:30. Yeah, we're just running 8 minutes behind.
Sorry, we were early.
No problem. Yeah, if you want to just pop off the call, I'll let you back in. Yeah.
Okay, thank you.
No problem. This is the problem when I just see a whole bunch of names in the waiting room. I just let everybody in.
Yeah. Okay, so we are paper 6-pack yolk or P6PY. And our team is Andrew, myself, Tiffany, and Leisha, and we are excited to present our progress on our design project with a focus on engineering analysis. So our problem statement is that 6-pack rings are not recyclable because facilities struggle with process complications due to the project geometry. Thus, 6-pack rings are rejected by the facilities and disposed of in landfills. So our goal is to design an alternative 6-pack ring that is able to be recycled or composted. And in the fall term, we selected molded pulp as our material of construction based on LCA analysis and consultations with industrial stakeholders.
And so at the onset of our problem statement, we require a 6-pack ring, or otherwise referred to as a yoke, that performs to the same or better degree than what is currently available. In addition to our final design, we require that the selection of not only a recyclable material be chosen that can easily be processed in the waste stream, but also a geometry that will not cause processing complications. Our criteria and constraints are not only governed by our customer requirements, that is those from beverage manufacturers, average consumers, and waste processors, but of the impacts our design will have on the economics, environment, and health and safety of the greater public audience. To help us accomplish the fulfillment of these requirements, various analyses and tools were employed to provide the case for our design. Performing field discussions with customers and stakeholders helped us understand the return on investment and public appeal, while statistical analyses of our material composition gave us understanding into what the best material blend will be. Life cycle impact assessments were also employed to help us actively quantify the environmental impacts our design will have in the market. And lastly, product modeling gave us leverage in understanding the best design to employ for our application. This network of tools, stemming from the simple problem our design aims to solve, was crucial for achieving our objectives.
So first, we completed some market research. Based on the results of our research, 74% of local breweries use HDPE or paper 6-pack rings or yolks for their beverages. Popular brands include E6PR and PackTech. They are likely popular because of their packing options, their specialty applicators, and their availability in North America. Almost 70% of these companies surveyed said that they would be open to switching to a different product if it met their needs. Many of their common needs include cost, ease of application, and environmental impact. Additionally, considerations that were not significant to the breweries or cidery were advertising space or specifics about size or weight of the ring. As cost was one of the most important impacts for breweries, typical costs were investigated. So you'll see on the slide that U-line LDPE is about 14 cents, and their rigid HDPE ring is about 40 cents. Competitive pricing of a similar product by E6PR is about 25 cents per ring. We're in the process of quantifying our production cost. So currently we have a material cost of about 5 cents a ring.
And so given the statistic that about 2/3 of small establishments rely on a renewable form of 6-pack ring, we have the market that our product will be viable and competitive. In further justification for pursuing our design, an initial environmental impact was performed in the grant to EduPack software by ANSYS, where embodied energy requirements for the material, manufacturing, and the end-of-life processes were evaluated. Focusing on these initial and end nodes of the product lifecycle allowed for a level comparison on why environmentally our product should be pursued. And so while these results may not seem revolutionary, the use of these tools are crucial in facilitating our verification over the progress of our design.
To develop our 3D design for the actual product, our group went through a few design stages. First, we investigated current products available on the market, as well as considered market research that we previously mentioned. And we used that as inspiration to produce several cardboard prototypes. From those cardboard samples, we then decided on one. We elaborated on the dimensions and curvatures we'd expect in order to fit a standard can. And then we began modeling this in a couple different renditions on SolidWorks, as you can see on the slide. We then proceeded to investigate the behavior of the product using FEA analysis on SolidWorks as well. So essentially in our FEA analysis, we based the properties of the product on cellulose paper, and then we simulated about 5.3 newtons, which is the weight of the can, a force weighing down on each of the can rings and calculated the reactionary force exerted by the fixed grip where your hands would be holding. As you can see, the stress analysis provides color mapping to indicate where the highest stresses are expected to occur on the product, and that would be on the ends of the grips. However, the yield strength scales on the right also show us that the forces don't exceed the yield strength where the product would break, which is good. It also allows us to animate the potential deformation of the product. So if you take a look at the orange outline on the bottom right image, this shows the original position of the product, and we can see how much the product may bend relative to that position. Since cellulose properties are similar to the materials that we have been testing in our lab, the results of a tangible product should be similar. However, using recommended manufacturing processes that can improve the performance of the material, as well as understanding the effects of material composition, we can reduce the amount of deformation, the performance of the product too. In terms of producing the product itself, we looked at the manufacturing process standard for molded pulp. Typically, molded pulp is produced in two main stages, and that's in the forming stage where water is removed from the pulp through a filtration process until solid content of the formed product is 40 to 55%. Then it goes into a drying stage where the remaining water content from the semi-formed product is removed, resulting in a finished product of about 4 to 8% moisture content, which is what it should be at normal room temperature. That said, we will be discussing different technologies used for these stages that could improve the product.
So looking at filter pressure filtration, we have investigated standard pulp molding processes. Andrew, can you scroll? Thank you. Sorry. However, sorry, my notes are gone. Vacuum filtration uses a vacuum through the filter membrane, whereas pressure-driven filtration uses applied pressure upstream of the filter. Both options have a variety of advantages and disadvantages. Given that the vacuum filtration is easier for mass production, better for drying, and has a cleaner operation, it is the optimum choice for production. However, in terms of the design of experiments completed in the lab, pressure filtration is ideal as is preferable for batch operation, easier to operate, and has low energy consumption.
After the pulp has been through the filtration method, the drying stages of plain molded pulp typically consist of oven drying. However, the most recent manufacturing approach in pulp molding is thermoforming. And thermoforming is a drying process in which the partially formed product from the filtration stage is captured in a heated mold, where it's also pressed, producing a densified product. Overall, this process provides a number of benefits, especially for our project applications. For instance, it's ideal for producing a stronger yet thin-walled product, which we'd like, and that's in part thanks to the pressing during the heating process, because that increases the bonding between paper fibers and improves the mechanical properties. The resulting products are much denser, smoother, and also more precise than the free-dried counterparts. However, the main disadvantage of this process would be that it increases the amount of electricity use, therefore increasing costs in terms of drying.
So in addition to the EduPack results, an LCA was completed that compares on-the-screen molded pulp, paper, and PET and LDPE. In terms of our product, it's a life cycle analysis from cradle to grave for LDPE and cradle to cradle for the others. As you can see, given the results of the production process of LDPE, this is to further be investigated in the next steps.
And we have planned a mixture design of experiment to study the response of the molded pulp's tensile strength, filtration rate, and thickness with regards to varying the amounts of each pulp type. With our results, we plan to plot a surface response and determine a polynomial from least squares analysis. And we can test the statistical significance of each interaction and also estimate the error. We completed each run in duplicate so that we could do the estimation of error, and we'll be using IBM SPSS to perform our statistical analysis.
Just a heads up that we're at 10 minutes.
So in terms of conclusions, so molded pulp was determined to be a suitable alternative for LDPE based on, as previously stated, the LCA analysis, the EduPack results, and industrial partners. Looking at our cost, in order to be competitive with brands such as E6PR, who have a cost of about $0.25 per packaging, we need to be competitive as well. Our current material cost is about 5 cents. In terms of pressure versus vacuum filtration is preferable for industrial production, as is good for continuous mass-based production. Pressure is preferable for the lab-based scenario, as we will be producing each set individually. The composition results are expected to be finalized in the coming week.
Perfect. Judges, any questions for them?
So people drinking beer sometimes spill their beer and then would get stuff wet. How would that impact the product? Or have you thought about how that might impact your product?
Yeah, so actually, initially, wet testing is definitely one of those things that we're looking into with our lab, in our lab work right now. But also, in addition to that, when we looked at the industrial processes, thermoforming, because it does make the products more dense, it actually makes them it makes the void fraction within the fibers much smaller in terms of there isn't as much interstitial space for the water to go through. So it should be able to withstand water fairly well, at least for the purposes of transporting it or keeping it in the fridge. Because thermoforming is also typically used for products such as plates and bowls that can also be based on cellulose. So in that kind of means it should be able to withstand some water.
Thanks.
Okay, I have a question. Other than that one, Jeff stole that one from me. We're even. Are there available, now what do you call your product? It's not cardboard, right, is it?
No, it's molded pulp, like egg carton material.
Okay, like a...
Like an egg carton.
Oh, egg carton,
Yeah.
thank you.
Yeah, so it'd be similar to like products like that are molded, such as egg cartons, or I believe even some types of paper plates or bowls.
Okay, and it would be good to have a direct comparison, especially when you talk about the plates being more water soluble. The egg cartons maybe not quite as much as the plates, but it might be nice to have that as a direct comparison, saying this is the sort of consistency we're looking at, and therefore, for example, water shouldn't be a problem. And is there something that exists on the market that uses this material, or is this a brand new application of the material?
There is. They're based in Mexico, though. So because of that, they have kind of different pulp fibers available. So it would have slightly different properties. We're using pulp sourced from Irving in Canada. And that was one of the things that we thought made our product more competitive in a Canadian market, was that the transportation would be less and the properties will be a bit different too.
Okay, and in terms of your finite element analysis, you applied a load which is equal to the weight of the can. That seems to be not, I mean, that's the minimum load, but it wouldn't be the maximum load. Have you thought about the loading application? Because at some point you want it to fail so that you can get the can out, but have you thought about what load that should be?
Yeah, and that really goes into part of the lab work that we're doing to find the optimal material blend. So right now our tensile strength testing is telling us or giving us an idea of what it should be able to withstand in terms of our specific material composition. specifics, that's around, for what we've seen right now, like anywhere around like 40 to 50 pascals, megapascals of force. So we're using that in our continual lab work to help find that maximum stress load.
Okay, first of all, that's a pressure, not a force. So that's a material strength, perhaps. But you should think about how much load you have to apply to the can to take it out. Right now, I think you've used 1G, just its weight. Obviously, you don't want it to fall out if it gets a little jerk and it just falls out. But at the same time, you want to be able to pull it out. So you should think about that number and what that should be. And it should be greater than 1, but maybe less than 10. Just out of the ballpark figure. But you should think about that. And I would personally try some of the existing solutions and figure out how much force you have to pull it out. And that might be a good reference.
Great, thank you, yes.
Quick question. One of the difficulties with designing products for end-of-life recyclability is the constant balance between making them easily recyclable and making them strong enough for in-service. What did you kind of prioritize in your selection of the pulp and maybe the final water content that will allow you to have enough retention at the sealing ring around the top of the can to make sure that the can doesn't fall out, as Professor Lambert said, and make it still recyclable in the end? Like, was it recyclability that was your priority, or really the strength?
So I think we prioritize recyclability a little more. I know in terms of strength, there's many chemicals that can be added to increase the strength and to increase the binding of the fibers, but we weren't sure how those chemicals would affect the recyclability. And due to the time constraint of this project, I think if we had like much more time to do it, it would be really nice to test out the different chemicals and see how that improved the properties as well as how much it affected the recyclability. But for the sake of this project, we focused more on recyclability.
Quick question for you. So you did the FEA analysis on the design of your rings. How did that analysis actually inform the design? Like what kind of iterations did you end up doing based on the results that came out of that analysis? Or did you make any changes? Was it just to validate?
So as much as it was to validate, we were also investigating the different product designs based off what we saw currently in the market. So our initial look at paper 6-pack rings that we can find at the store, we were just simple application, like what was good or bad in holding it, what was good and did we find in the positives and negatives of it. And so our design, we want to just have that verification on, will any changes we made to what's existing be able to withstand the expected forces and loads that we're trying to have while we use it.
Alrighty. I think with that, we are out of time, but thank you so much, everybody. And best of luck with the rest of your 4B term, the rest of your capstone.
Thank you. Thank you for all for your time today.
Thank you.
No problem.
Thanks a lot.
Hello, everybody.
Hello.
I guess just so I don't make the same mistake twice. So this is air motion pen, right?
Yes.
Okay. Anyway, this is everybody we're expecting, I guess? Okay, perfect. So we'll do just a quick introduction of the judges, and then I'll turn things over to you folks to present, and we'll sort of go from there. Steve.
Hi, Steve Lambert, Mechanical and Mechatronics Engineering.
I'm Jeff Abshoff. I work at ANSYS in development.
Andrew Griguch, I'm in Mechanical and Mechatronics Engineering.
And I'm Chris Rennick from the Ideas Clinic. So with that, it is 3:58. So I'll give you a 1-minute warning in the chat when you sort of hit that time, but otherwise you guys can share your screen and take over from here.
Awesome, thanks. Just a bit of background, all of us are also in mechatronics engineering and doing this for our 4th year design capstone. Sorry, is the screen showing for you guys? I currently see a white screen.
Blank for me too.
1 second.
There we go.
Can you guys see it?
Yep.
Yep.
Perfect. Let's get started.
So, hello, we are the Air Motion Pen group, and we'll be talking about the analysis performed throughout our project. The purpose of this project was to create a peripheral device that combined the functionalities of an optical mouse and a digital stylus with minimal platform dependencies. This resulted in the creation of the Air Motion Pen, a wireless device that incorporates both these functionalities without the need of any additional hardware. In other words, this is a mouse and stylus that you can use in the air. So how did we achieve this? We implemented a Bluetooth connection and an IMU sensor to wirelessly obtain 6 degrees of freedom inputs and detect the motion of the device. Using these inputs, we leveraged machine learning to create a gesture recognition model to translate the motions and gestures performed by the user into stylus and mouse functionalities. Next slide. Translating the motion of the device and developing the gesture recognition model required significant amounts of analysis. The analysis that we will be discussing today helped us verify the feasibility of our design by analyzing the MPU orientation, the model precision, and latency. Additionally, it verified the implementation and assisted us in fine-tuning the controls behind their functionalities.
In this part, I will be performing the MPU orientation analysis. The MPU contains an accelerometer that measures the translational acceleration along each direction in meters per second, and a gyroscope that measures the angular velocity around each axis in degrees per second. We would like to use MPU as the only sensor for cursor control, which needs screen coordinates as an input. Therefore, the MPU should provide either global 3D coordinate position estimation or orientation estimations of itself. With a lack of global coordinate information, the MPU alone cannot measure translational motions. So the objective is to use MPU readings to estimate its orientation at a timestamp. Since angular velocity is known, the rotation in angles can be measured by taking integration over time. The accelerometer itself can also be used to estimate the MPU's orientation, which can be fused with the gyroscope estimation through the complementary filter. Lastly, the metric algorithm could theoretically estimate MPU's orientation in quaternion angles. These 3 options will be analyzed separately. Option 1 defines a small time interval to perform integration, and the time interval is the sampling interval of the MPU module, which is 1/700 seconds in our case. Sampling, the integration computes a change in rotation angle around a specific axis, and the change accumulates for every timestamp to compute the actual Euler angle. Option 2 makes use of the accelerometer readings, which has a constant gravitational acceleration of 9.8 meters per second. When the MPU stands still horizontally, accelerometer will read 1 g of acceleration in its z-axis. When the MPU is rotated, its gravitational acceleration will be split to x and y axes, which could be used to compute Euler angles through trigonometry. Option 2 then takes the estimation from option 1 and fills the estimations through a weighted sum, where results from option 1 has a much higher weight than the other. We took a recorded gesture of rotating downwards, which should return negative Euler angles around the y-axis. The blue line demonstrates estimations from the accelerometer, which does not work correctly. This is because the accelerometer estimation requires the accelerometer to remain still without external force. Any external force will create extra accelerations, mixing up the gravitational acceleration and confuse the algorithm. Option 1 does perform well in this scenario with correct estimations of the Euler angle. Option 3 also takes in both accelerometer and gyroscope readings, and it returns the orientation of the MPU directly in the form of quaternions. The quaternion angles can be converted to Euler angles for evaluation purposes. We fed the algorithm with the same up-to-down gesture readings, but the algorithm demonstrates weird behaviors. We suspect that the precision of our MPU is not high enough as its accelerometer readings drift a lot. Based on our current hardware and expense, we applied option 1 in our final design.
Next, I will talk about the machine learning model precision analysis. For the precision analysis, the objective is to evaluate the model's accuracy on predicting the user's hand gesture motion to ensure the feasibility of the model. The methodology for evaluation is we first train the machine learning model on 80% of the collected data and test on the rest of the 20% of the data. The overall accuracy of the prediction is the number of correct predictions divided by the total of the test cases we have. For the individual class prediction accuracy, we construct the truth table to record the corresponding true labels of different gestures and the corresponding predictions made by the models. And to evaluate the corresponding precision accuracy, we have 3 different variables. First is precision, which use TP divided by TP plus FP. Recall is just TP divided by TP plus FN, and the F1 score is just the combination of the precision and recall. The table just gives an illustration of how gesture 1 defines the true positive, false positive, and false negative. Initially, on the 80% of the training data and 20% test data, the overall accuracy of our model is 100%. Correspondingly, the precision, recall, and F1 score is also 100% for each gesture class, which is really high. And to explain this, we verify our accuracy by visualizing the corresponding MPU readings. These 2 figures are just the circular gesture motion collected from 2 different users. As you see, the accelerometer and the gyroscope readings have similar trends, which verify our accuracy of the model. But we have a question. What about the model's performance on some data that it never seen before, such as the new user data? So we continue our evaluation on the new user input. So previously, the 80% of the collected data set consists all gestures from all users. So we need to evaluate the prediction accuracy on type of data that the model has never seen before. Now we construct a new train test split. So test on all the data from a single user input and train on the rest of data from the rest of the users. And now with that strategy, we evaluated from our model on the test set. The overall accuracy decreases from 100% to 73%. And the model shows relatively poor performance on gesture 0, 3, and 5. This also gives our indication that the model does not perform really well on new user input specifically for these 3 classes. So in the future, we can fine-tune the model with more diverse gesture data for those 3 classes. Next, we took a middle ground where the model sees only a limited user input. Unlike the previous case where the model does not see the new user data during the training at all, what if the model only sees a few of the training of the data sets? Less than the original of the 80%, of course. Will that improve our overall prediction accuracy of 73%? Well, the answer is yes. Next, we start with the evaluation by including 20% of the new user data in the training data and use the rest for testing. The overall accuracy of the model prediction increases from 73% to 84%. And the prediction accuracy for class 0, 3, and 5 also got improved. Next, we include 30% of the new user data in the training data and use the rest for testing. And the overall accuracy increases from 98%. And all subclasses accuracy shows significant improvements. In conclusion, with only a fraction of the new user data, the model is capable of capturing the characteristics of the new user gesture's motion and output accurate predictions. Therefore, our gesture recognition model is feasible to accurately recognize a user hand gesture motion. And with additional of a small fraction but diverse gesture data, we could fine-tune the model as well. Next, we continue with our model latency analysis. The objective is to evaluate the time of the model takes for each prediction to analyze the feasibility for real-time gesture recognition. The methodology is just to time the period between the model's inputs the gesture data and outputs the predictions. We repeat these measurements for 10 times to reduce the measuring bias.
Just to note that we're at 10 minutes now. So if you could kind of move towards wrapping things up.
Yes. So this is just the latency measurements we have for the original model, which the latency is about 0.13 seconds. Size of the model is 1.3 megabytes. And then we apply some quantization techniques to reduce the model size and the corresponding latency. The technique is just to convert the 14.32 bits integer format to integer 8 bits. So the conclusion is just the post-training quantization allowed the model to inference faster while significantly reducing the model size. It also preserved the original prediction accuracy. So the latency analysis proved that our real-time gesture recognition function is feasible. So that is for our presentation. Thank you, everyone. Is there any questions?
Thanks. Yeah, any questions from the judges?
It was interesting with one of your, when you did the 20% data, it looked like one of the motions prediction went down to 0.22. Motion
Yes.
4 there.
Actually, yeah. I think you're referring to number 4.
Yeah.
Right. Yes, this is, I think it's just like, since we are randomly initialize the model from with random initialized weights, this could be just be a coincidence. If you see the overall accuracy and also the rest of class, that the overall accuracy got increased.
Mhm.
Yes, so this might just be a coincidence in our experiments.
And so you have these 6 gestures, were they were the same gestures every time?
No, there are total of 7 gestures. So we define them, for example, from left to right, right to left. So each of the 7 gestures are different.
Sorry, but I meant 0, 1, 2, 3, 4, 5. Those are the
Yes,
7
yes,
gestures,
they're
and
the
between
same,
each of
yeah.
your analyses, you were using the same 7 gestures.
Yes,
Okay.
yes, that's right. You can interpret it as they are the corresponding gesture labels we assigned.
Was there an 8th gesture that you didn't use, or 7 gestures, are they representative of everything that the pen would move?
So for our purpose, we only include 7 gestures for the model to recognize, which I think for our error motion project, pen project, it's enough to define several interesting characteristics for the users.
Just for reference, the gestures that we did were up and down, or sorry, up to down, down to up, left to right, right to left, roll left, roll right, and also a circle motion. So those ones encapsulated pretty much all the main characteristics that we thought were relevant to the project.
What about forward and backwards?
I believe we did not decide to implement that just because one of the other use cases of the gesture recognition was to associate it with customized functions. So let's say you wanted to do like a custom input. So let's say map it to a control V, like a copy paste. Then we figured those would be a significant amount of gesture location mappings so that we could actually associate them.
And how big were your gestures?
Well, the gesture itself is just a really a short period, like a sweep, like goes like this.
Okay, but you've just moved your hand what looks to me like 6 inches. Versus if I'm writing and I do a little sweep, it's, you know, a quarter of an inch or less. What's the order of magnitude of your gesture? Because certainly that will have something to do with the magnitude of your signal responses, right?
So in terms of the motion of our gesture, let's say that we are performing the left to right swap sweep motion. So this one will correspond to an angle of rotation around the z-axis of about 90 to 100 degrees. to this much. This is different from a normal like tiny sweep when you are writing.
Okay, so this is not, for example, you can't use this as a virtual actual pen, right? It's more like sweeping the motions like Star Trek.
Here, let me make a clarification point. So we have our gesture recognition, and we also have a separate functionality for cursor control. So essentially, we had a functionality on the actual device where you would double click the buttons. That way, it would enable the gesture recognition so you could do the motion detection. Whereas if you didn't have that enabled, then it would just be a regular cursor control. So you could just do more smaller motions without actually interfering with, oh, we're doing a sweep motion every time.
So you're installing shortcuts, Control C, Control V, quit, escape,
Yes.
enter.
Exactly.
And those are large motions, is what you're saying.
They don't.
Relatively larger, but still within like a
Not the whole
wrist
width of
twisting
the
motion.
room. Sure.
Yeah, you don't have to hit someone.
So in our data pre-processing, we actually do some interpolations and also upsample our the MPU readings. So for example, if you do from like 1 inches, 2 inches, or 5 inches, after some upsampling, the data won't make a huge difference, especially after it goes over like 5 or 6 inches of distance.
So the very initial training set that you used, was that something that you folks created? Like, did each of you grab the pen and make each motion 10 times and built a data set that way?
Yes. So we have we have several group members who actually sit down and grab the pen and record different gestures, and we also create the data sets and save them, do some pre-processing, and use that as our original training sets.
Was everybody right-handed?
Yes. Currently, we only have like right-handed supports.
One of the things I get, like, I guess my question is, who's the user for this device? Like, what was kind of your target market? Like, I could see Professor Lambert at the front of the room. If he's going through his lecture slides, he might want to be able to swipe the same way. But who is your actual sort of target for this?
Yeah, so our target was just a general audience that wanted to have more of a compact device. So, for example, one of the things that we noticed just going to classes sometimes is when we go into class and use something like AutoCAD or SolidWorks, if you did not bring your own mouse, it's kind of a difficult thing. You're using the trackpad, you can't really do a scroll motion that well, or there's some things where you want to use a stylus to just write something pretty quickly, but it's kind of hard to do with a mouse. So we were thinking, why don't we combine these things together? But then we looked also at what was available, so like the Wacom tablet, where technically you can plug it into different devices and associate it there, but you still have to have a tablet functionality as well. And like, we kind of just want to put everything in one, so you only have one piece of hardware that you ever have to bring with you. You don't have to remember anything else, and you can use that literally to use a touchscreen, or you can even just use it while writing on your desk or in the air motion. Everything goes. So
will your device then, like, if I'm at a whiteboard, say, and I'm kind of making the gestures with that frame of reference on a vertical wall versus like I'm doing it on top of a tabletop, the pen has rolled, 90 degrees from one sort of board orientation to the other. Will your device still read a right to left sweep the same way if I'm doing it on a tabletop versus on the wall? Do you know what I mean? Like, you're going to hold the pen differently, basically, and the motion is going to be in a sort of a different like reference frame.
Well, in terms of cursor control, our reference frame is fixed such that the z-axis, which is the top of the pen, should be pointing upwards. So in terms of the cursor control, yes, the pen position needs to be fixed. But in terms of the gesture recognition, our model can be user adaptive. So for different holding positions or different scenarios, as long as we give it, for example, 3 sets of data for each gesture, it will memorize what you have it will memorize the current scenario and the pattern of your input, and it will classify the correct gesture that you are inputting.
Okay.
Quick question. You mentioned the training data that you generated. Is your TensorFlow platform, is it referencing an open source library that's much larger than what you're using? And I'm curious, if it is, what implications are there to the NPU and the accelerometers, like the physical hardware that you've selected and the filtering that you're using on your sensor data? How does it kind of translate and map to that larger data set?
So I will go through our data pre-processing pipeline. So basically, the IMU sensor will read the gyroscope data and accelerometer data, and we basically will collect it and then standardize it. Standardize by meaning, for example, we go through the whole gesture process, and then we'll find the means, find the standard deviation, do the standardization, and then do some using the SciPy's zoom function to use interpolation and upsample it to a length of 4,500. So
Okay,
basically,
upsampling is what I was asking. Perfect. Okay.
Yep.
Thank you.
No problem.
Sorry to cut you off.
For the previous question that you asked about the reference frame, yeah, I saw about it again, and about the cursor control, I was wrong. Our stylus does not need a fixed reference frame for the cursor control, nor the gesture recognition model. The cursor control can be performed with different holding because the reference frame is relative; it is not global. The reference frame is relative to your hand, for example, your wrist, your thumb. So we have defined the holding position, and it is ergonomic. That is why even with a different holding position, say you are holding our pen that is pointing to the screen, or you are pointing this way, or you're pointing this way, the relative reference frame does not change. So yes, it can still control the cursor, and we have tested this before.
Alrighty. I think with that, we're out of time, but thank you so much for presenting, and best of luck with the rest of the term and your capstone project.
Awesome. Thanks for having us.
Thank you. Bye.
Thanks. See you. Hey, everybody. Oh, I think you're muted.
Oh, there we
Rachel.
go.
Yeah.
Hi.
Hey, everybody. Sorry, we're running a little behind, as is typical, I guess, of university things. So I can see Steve's chair, but I don't see Steve. So I might, should we wait for him to get back or just do introductions? Oh, there he is. We'll do a quick round of introductions of the judges, and then we'll turn things over to you folks for the presentation. So you'll have 10 minutes for the presentation, and I will give you a 1-minute warning in the chat, and then we'll do a Q&A after that. Yeah, I guess, Steve, if you want to introduce yourself. You're muted, by the way.
That's why it didn't work the first time. Steve Lambert, mechanical engineering.
Hi, I'm Jeff Abshoff. I work at ANSYS in development.
Andrew Gerguchin, mechanical and mechatronics engineering.
And I'm Chris Rennick from the Ideas Clinic. So with that, if you folks want to share your screen, if you've got some presentation slides, you can take it away. And it is 4:23 now, so.
Okay. So yeah, hello everybody. So we reduce carbon and absorb. We're here to talk about our PET plastic to activate carbon conversion analysis. Our team is composed by Rachel Blanchard, Nicole Howard, Chris Ma, and myself, Steven Bulcacundo. Our faculty advisor is Dr. Chris McKenna. So now moving on to the introduction, we will briefly discuss an overview of the project and also discuss some of the objectives of it. Do you know that around 480 billion bottles are used worldwide per year, but only 29% of this is actually recycled? And from that, a large portion of that is either shipped overseas, incinerated, or end up in the landfill. Therefore, as a team, we want to design a process to carbonize PET into activated carbon to divert plastic from the landfill and improve the sustainability of PET disposal, while at the same time creating an optimal product for chemical industries that utilize activated carbon for dye absorption process purposes. Regarding our criteria, two pillars of the process success are high sustainability and high cost effectiveness. This will be verified through engineering analysis, laboratory experimentation, and modeling. Now, regarding our objectives, we want to validate our scale-up PET to activated carbon production process. It's both sustainable and cost efficient. We also want to use available software to verify results, also considering the cost of it. And finally, we want to conduct laboratory experimentation to inform greenhouse gas emission and cost models. We now move on to the analysis.
Thanks, Stephen. So next I'm going to talk about the experimental analysis. So to assess our product as a dye absorbent, we carried out some tests to validate the performance and cost of our process. First, we used BET surface area analysis as an indication of the key performance property of surface area, which is theoretically directly related to absorptive properties. Next, FTIR testing was used as validation of the conversion of PET to activated carbon based on absorbances associated with PET structure as an indication of required reactor conditions. Next, zeta potential was used as another performance indicator since it relates to the surface charge. This indicates if our sample can effectively absorb cationic dyes such as methylene blue. So first, our FTIR results validated the necessary conditions such as temperature and time to achieve full conversion of PET to activated carbon, as indicated by the complete losses of the characteristic peaks of PET as seen here in our results by using conditions of 800 degrees and 2 hours. This validated the required reactor conditions for full conversion to activated carbon. Next, the performance of our product needed to be validated first by testing of the zeta potential, since this relates to the surface charge. As you can see from our obtained results, we confirmed a negative surface charge of all of our samples, which indicated the capacity to absorb cationic dyes such as methylene blue through electrostatic attraction. And next, we also calculated the surface area through BET analysis as another indication of potential absorptive capacities. This was then compared to other industrial products to ensure that we're meeting the high industry standards around 1,000 meters squared per gram of surface area, which we were, and then we validated these performance properties through methylene blue dye testing. And as you can see from the blue bar charts, our product is actually performing above other commercial products. Nicole will now talk more about the dye absorption testing specifically.
Thank you, Rachel. So now I will be discussing about the dye absorption results of our experimentation. As shown on the visual on the left, our overall objective was to achieve 100% dye recovery of methylene blue dye, or completely separate the methylene blue dye from the wastewater. As shown by the samples, the visual, we see our reactor conditions of our activated carbon product at 800 degrees Celsius in 2 hours was able to meet that objective. We further optimized our results by looking at the methylene blue number. Now what that is the amount of methylene blue that is absorbed divided by the amount of activated carbon utilized. We were able to achieve a number of 447 milligrams of methylene blue absorbed per gram of activated carbon, directly relating to the performance of our process. The main reason why the dye absorption testing was utilized is a form of validation, especially for a proof of concept validation of our prototype or our activated carbon. And secondly, our activated carbon performance was directly related to the cost of the scale-up. A higher temperature would cost more in the scale-up process. So now, Chris will talk about the analysis of our modeling.
Thank you, Nicole. With the promising data collected during experimentation, we have developed a scaled-up PET to activated carbon process and quantified if the process is sustainable and cost-effective. We analyzed these two factors by investigating process greenhouse gas emissions and process economics. Greenhouse gas emissions from the process were calculated through both FDIR and carbon yield results collected from experimentation. To compare our emissions with both PET disposal methods with other PET disposal methods such as incineration, we analyzed incineration LCAs using a software named OpenLCA. A cost analysis is also done on the process. Capital and operational costs are calculated through industry-established methods. Profits are estimated by comparing our activated carbon products' performance as determined through experimentation, through BET surface area and zeta potential measurements with similar activated carbons on the market. Since the calculated emissions of our process is crucial for process feasibility, we explain the basis of our emissions model. A large portion of greenhouse gas emissions are emitted from our process's reactor, which converts PET plastic to activated carbon. A scheme of the process reactor can be seen in this slide. Through data collected through experimentation, we can fully define the activated carbon solid flow rate that leaves the reactor. However, the composition of the gases released will still be unknown. Through literature review, the gas composition can be estimated, and through carbon mass balances, the flow rate of the gases can then be calculated. This allows greenhouse gas emissions to be determined. The estimation of our gas compositions will be validated later on. Our results show on the left that our process emits significantly less greenhouse gas emissions per day than alternative methods of PET disposal, incineration. We also show that our process produces less greenhouse gas emissions than other established methods of activated carbon production, namely activated carbon produced from coal and biomass. Cost estimates of our process show a payback period of around 1 year of operation, even after the inclusion of a contingency. Compared to expected process lifespan of 10 years, we see very high potential in our process, with costs not expected to hinder our progress. So both greenhouse gas emission and cost models were validated to ensure accuracy. The total mass entering and exiting the reactor should calculate to be the same based on mass conservation. In addition, all elements such as hydrogen that go into a process must also be conserved. This consistency check showed acceptably low errors in our calculations, which in large part verify assumptions made in our emissions model. Cost estimates were validated through the utilization of alternative cost estimate models, such as the Icarus economic model. There is good agreement between our results and calculated ones. Lastly, operational costs, especially that of energy usage, was verified through Aspen enthalpy calculations.
Chris. Now I will talk about the conclusions and final remarks and impact of our project. Throughout our experimentation, we were able to verify the two main pillars that we focused on, high sustainability and high cost. We were able to complete further additional progress in the project through these pillars. Many of these results were verified utilizing engineering fundamental principles, as well as analysis software such as OpenLCA and Aspen Plus. We will continue to verify these results through subsequent experimental and pilot scale testing. These results facilitate additional projects to improve marketability and effectiveness of our process, including optimization studies, portfolio diversification, and market research. Thank you for taking the time to listen to our process about PET conversion to activated carbon conversion analysis. Thank you so much, and we look forward to answering any questions you may have.
Thanks. Any questions from the judges?
You talked about modeling the reactor, how was the modeling actually done to get the greenhouse gases?
Yeah, so I can explain a bit about that. So could you please go back to the slide, the reactor? So specifically what we did is we did a carbon mass balance. So through our experimentation, we were able to determine the yield of carbon that is released by the reactor in terms of the activated carbon solids that were produced. So as you can see in this diagram, we actually were able to define fully the solid emissions that were produced from the reactor. But we didn't know the gas emissions, and that's important for greenhouse gas emission quantification. We used literature review to estimate the composition, and through the carbon mass balance, we were able to determine the amount of gases released. And it was verified later on that our compositions were correct.
Sorry, and how did you verify it?
Yeah, so for greenhouse gas emission modeling, we use the basis of making sure that the carbon mass balances were satisfied, right? So carbon going into a reactor must equal the carbon going out of the reactor. That's how we determine the gas flow rates. But we also consider other species balances. For example, not only carbon must be conserved, but also hydrogen. So that was checked for consistency. We also checked the overall mass balance. All the mass that goes into the reactor must equal all the mass going out. And that was checked for consistency as well. And that partially helped verify that our gas compositions that we assumed were correct.
Thank you.
Can you go back to the slide where you were showing the blue dye absorption testing? I just want to make sure that I understand what you're showing me. This is the problem when you get no chemical engineering people in the room. So with this, you were just trying to kind of do an initial validation on the activated carbon that it was basically working as activated carbon. Is that kind of the point of this?
Yeah,
Yes, Chris.
yeah, just to show that it was achieving a surface area that would absorb enough methylene blue dye.
And so this was kind of dialing in, it was temperature, right? Was kind of your main variable here?
Yeah, we screened through temperatures first, 600, 700, 800, and then once we chose 800, we looked at 1 hour, 2 hour, and we saw 800 2 hour was our best sample.
Makes sense.
And I just wanted to add on to that point. We also did dye absorption tests because we wanted to develop an optimized scaled up process. Because we wanted to, first of all, minimize the time that activation would occur to minimize operational costs. And we also wanted to see, well, we also wanted to develop a high performance material that could sell well as well. So these results were also very highly linked to cost estimates that were done.
How novel is the process that you folks are proposing? Has anyone tried this before?
In research, yes, there's no process in industry using PET as a feedstock.
And if I can add on to that, the ones that are mostly in industry are made from coal and the biomass.
Yeah, biomass and coal. Yeah. And so like the conditions we use, we also have sort of different conditions than in other research papers, like not many looking into varying the activation time and using a low level of KOH in our process for activation, like 1-to-1 ratio we use, which was pretty impressive since a lot of other researchers use a higher amount to get higher surface areas.
Any questions from Andrew or Jeff?
How much of a difference is the surface area to volume ratio of your, I guess, the dye? Like how miscible is it in the other fluid that's in the mixture that you have?
Oh, yeah, so the activated carbon is quite hydrophobic, so it does require mixing to get it in. For the purposes of our testing, we had to kind of make everything consistent. So we did sonicate briefly before our tests, but we did do testing of just adding it in directly in a dry form, and it worked completely well for our 800-degree 2-hour sample. So we think mixing agitated tank would work just fine.
Alrighty. Any other questions? Nice. Yeah, nice job, everybody. I think with that, we'll let you go, but thanks so much for presenting for us, and best of luck with the rest of your 4B term and your capstone project.
Thank you very much for your time.
Thank you. Thank you so much.
Thanks.
Bye.
See you. All right.
4 more.
Thoughts? I suppose there's a few different ways of doing this. I have sort of a fairly clear, I think, top 4, maybe top 5. I don't know if it would be worth sort of going around and seeing if we all agree at least on that, and it will give us half as many teams to talk about. That kind of makes sense.
Sure.
So for me, I think our origami, the first one we saw, was quite strong. I think the endoscope group was quite strong. Magic window was pretty good. I like that one. They certainly knew their stuff. And this last group actually was really good as well. I think the wind protection on the bridge is probably my 5th. Does that kind of jive with others? Those weren't really in any particular order, but
I think that's similar, probably.
I'm going to need a minute to compose my thoughts, which means get my spreadsheet done.